Good morning, I'm Manuel Zarzo, and here we are continuing with the Unit 7 analysis of variance, and here I'm going to present three exercises about application of ANOVA. This exercise, number 4, is a replicated experimental design 2 part to 2, which means 2 factors at 2 levels. It is a chemical reaction where we intend to improve the quality of a mixture used to incorporate a certain additive in a polymer. Okay, so we have that the response variable is the percentage of additive that we want to maximize. So we have 2 factors, which is the stirring speed in the mixing process and the stirring time. Okay, and then these are the experimental results. So we have 4 treatments and 3 replicates, and so if we multiply the 4 times 3, this is the total number of values. We analyze them with ANOVA, and in the next slide is the result that we get. Okay, so good. This is the ANOVA table, and the most important information are the p-values. So here we have time, speed, and the interaction between them. So first we can see that the effect of the double interaction is not statistically significant, okay, because the p-value is very high. It is much higher than 0.05. But we can see that the effect of speed is statistically significant because the p-value is very small, less than 0.05. But here we have that the p-value for time is 0.084. Well, so it is bigger than 0.05, so strictly speaking, we cannot reject the null hypothesis, but anyway, we are close to this threshold value of 0.05. So we should take that into account. So the effect is nearly significant, clearly significant, and no evidence about the interaction. Well, these are the LSD for speed, as we reject the null hypothesis. Okay, so it is consistent with the fact that the LSD don't overlap. In this case, as we want to maximize, we should choose the highest speed, which is 1000. And for time, this is what we have. So as the effect is nearly significant, we have a slight overlap between both LSD, which are obtained for 95% of confidence, which means that alpha was 5%. Okay. Anyway, in this case, as we want to maximize, we will say that we would choose, so if alpha is 5% and then as the p-value is bigger than alpha, we can say, well, we cannot reject the null hypothesis, and then it doesn't matter to choose 33 or 6. But if we consider that the effect is nearly significant, we can say maybe it's better to choose 3, okay, because it seems that probably on average the response variable will be higher, and interestingly it corresponds to the lower time. So lower time means that we are saving time, and that is convenient from an industrial standpoint. Okay, so what I was explaining, as the effect of time is nearly significant, it seems convenient to take that into account. So those are the optimum operative conditions: speed 1000 and time 3 minutes. Good. So now this is another exercise. It is a factorial design called 2 power to 4 minus 1. The minus 1 means that it is a fractional factorial design where we're carrying out 50% compared with the complete design. So here in this case we want to study the effect of 4 factors in the stability of a chemical product. We want to maximize the stability of this product. And these are the 4 factors. Concentration of acid expressed in percentage. So the minus symbol, or the lower level, for this factor will be 20% of concentration for acid, and the plus, or the higher level, will correspond to 30%. Another factor is concentration of catalyst. Okay, so the lower level will correspond to 1%, and the higher level will correspond to 2%. And for temperature, when we put the lower level will imply 100 degrees, and when we put the higher level will correspond to 150 degrees. And finally, the fourth factor is the concentration of monomers. The lower level will be 25 and the higher level will be 50. Good. So this is the experimental design. We have the 4 factors, and then we run the 8 trials, and this is the response that we obtain experimentally. This is the stability. So we introduce this data in star graphics. We analyze them with ANOVA, and this is the ANOVA table that we get. So here we can only study the simple effect of the 4 factors. Actually, we can see that the degrees of freedom of the residual is 3. Remember that this is not enough. The minimum required to get reliable results is 4. Okay, but then we can see here, so we can see that this p-value is much bigger than 0.05, which means that the concentration of monomer has not a relevant effect. Okay, so we remove that factor from the ANOVA and then we repeat the table. Okay, but conversely, the effect of catalyst is clearly significant, and the same for the effect of acid. In the case of temperature, the p-value is close to alpha. So as the degrees of freedom is so small, so we decide to remove temperature and monomer, and then we decide to leave in the ANOVA just acid and catalyst. Now we have 5 degrees of freedom in the residual, which is enough, and then we get that the p-value for acid and catalyst is much lower than 0.05, so we say that the simple effect of both factors is statistically significant, which means that we reject the null hypothesis in both cases, which means that the average of acid at the population level will be different from the lower to the higher level, and the same that the average of the response variable will be significantly different at the population level if we compare the higher level versus the lower level of the catalyst. Okay, so now I leave you as an exercise how to determine the optimum operative conditions. So, so you have to decide which concentration of acid to use and which concentration of and which type of catalyst. So for temperature and monomer, it doesn't matter. Probably it would be more convenient to use the lower temperature and maybe the lower concentration of monomer, but that would be for technical reasons, but not statistically. So from a statistical standpoint, we have to say that it doesn't matter to choose one or the other level of temperature of monomer. And for the case of acid and catalyst, we have to choose one level is the better. And for that, you have to go to the data and compute the average value of the stability that we obtain with the lower value of acid, and then you have to compute the higher level of stability that we get with the higher level of acid. And then, as we want to maximize, you have to choose the level that leads to the higher stability. And then you have to do the same for catalyst. I give you this as an exercise. Well, and then finally, for this 6th exercise, we have 5 factors that are studied to improve the yield of a chemical process. The target is to maximize the response variable. Okay, so this is the experiment. We have, these are the factors that are called A, B, C, D, and E. Okay, we want to maximize, and then these are the experimental data that we have. Well, what we can do is to, well, in total we have 32 experimental data, which is quite a lot. Okay, imagine that if this is a real experiment, carrying out 32 trials sometimes is expensive, and also it can be time consuming. Okay, so this is the ANOVA result with the 32 values. Okay, and then we can see that we have B, C, D, E, and then the interaction between C and D which become statistically significant. The simple effect of A has been removed, and also the other double interactions have been also removed because they were not significant. you can see here that the number of degrees of freedom of the residual is very high, okay? 26 is much bigger than 4, so we have a lot of degrees of freedom, and so that is good. And also we can see that the p-value is very, very small, which means that the simple effect of these 4 factors, as well as the effect of the double interaction between C and D, is significant. Okay, what would happen if we had only performed 50% of the trials? Okay, so based on the previous slide, which is here, now what I'm going to do is to select only those values which are in red. Okay, this is a fractional factorial design where we carry out just 50% of the trials. How are these values? What is the criterion to select these values in red? So the criterion is that we multiply the signs. Okay, for example, -1 multiplied by -1 is 1, 1 multiplied by -1 is minus, minus multiplied by minus is a plus, plus multiplied by minus is minus. Okay, but here, if we do that for every row in red, if we multiply the signs, we will get a value plus. So the criteria is that we are going to select those rows where if we multiply the signs, we get the value plus. Okay, that is the way to perform this analysis. And then if we do that, so I'll give you this as an exercise. You have to fill the ANOVA table. Well, remember that this can be like an exercise for the exam. We have the total sum of squares for the factors, for the interaction, so you have to compute the residual sum of squares, then you have to divide, get the mean squares, then the F ratio, and then to compare the F ratio with the critical value from the Fisher's table and decide which of them are statistically significant. And then you will get that more or less we are getting the same conclusions as we work with the complete design, which is interestingly because just working with half of the trials, which means that we save 50% of the money, 50% of the time, we are getting basically the same information. Okay, so which is good. And this is the final solution. Okay, I give you also this is an exercise, but this is the final solution that you should be able to get. And then here I finish this video about 3 more exercises about application of ANOVA.